So the today's subject is dual simplex method. So this method is very important because it's coupled with the simplex method, and right now MATLAB have joined the dual and the simplex method in one algorithm, so it will reduce the computational effort to have the optimal solution, and also it's solve many problems you have seen in a previous solution. So basically any simplex method can be seen as two mathematical problems. These two problems are coupled. So when you solve, for example, the original problem, you will have also, let's say, imagine that as a negative a problem, or like an inverse in somehow kind. This is a problem, and solving the negative problem will give you the same state variable from the original one. So in optimization, we call the original uh, problem the primal simplex. And basically, when you formulate it, it can be a maximization or minimization. So regardless of your problem, how you see it, generally speaking, most of the optimization problem are minimization. So it will be maximization of the sum product of the cost or the profit by the variables you have. Then you will have a set of constraints. Basically, we still having a continuous variables. So this notation should be j. So j is sorry, this is xj more or equal 0, and j will be the assigned variable. So it might be 1, 2, up to n, and you have m of equations. So you have n of variables, then you have m of equation, which is very important. So when you have the dual problem will be set as a minimization. So if you have a maximization, then your dual problem will be a minimization of W. So right now I have denoted with W to not just miss it with the previous one when we called maximize of Z equal minimize of negative C. So this is another thing. So forget about what we have taken in simplex when we switch maximization into minimization. This is a totally different thing. Then your weights for this equation, so your variables here, instead of having set of decision variables, these will be denoted of your constraint. So for example, the original primal simplex have a 3 constraint, then you will have a 3 decision variable. So you will have a ya1, a y2, then y3. So this is depending of how many constraints. And bi here will be the same. This the right hand side will be the coefficient for your state variable. So for example, let's see a problem very briefly and go back to this notation. So if you have a, let's say, a maximize of z equals to 3x1 plus 3x2 subject to, this is the first constraint, this is the second constraint, this is the third constraint. So your minimization problem will be minimize W. So originally we have maximize, the problem became minimize. So the coefficient of or the cost for your decision variables in the dual will be how many constraints you have. So we have here y1, y2, y3. So we have 3 constraints. Then it will be subject to, so it will have the same coefficient what we have here in the original primal simplex, but you will not in this equation you look to the row, this time it will be as a column. So these guys will be changed from how you look to the problem in this format, and then you will look at in column, and we will see the problem to sometimes the student is not like happy with this kind of notation. Then here, what we have previously as a cost or a profit will become the right hand side for our dual problem. So basically, what's the dual simplex method doing? Sometimes you stuck with invisibility in maximization problem, but you know you have a solution. But for this step, you have, let's say, an invisibility solution in that step. So to override it, we have this dual simplex. So someone can tell me what is the main difference between, like, just a quick look to the maximization problem and minimization problem. What is the missing between these two equations? So what's make the primal as a primal, and what is missing in the dual simplex? Just look everywhere over here and you see something is missing for the dual simplex method.
In the dual, it doesn't have the non-negativity.
Yes. So to override the invisibility, we make our decision variables free. So it will not having any non-negativity constraint. So we can continue our solution, and we will see how this method is working. So the first thing is to know how to change our primal simplex method into dual simplex method. So this is the basic idea, and this is the most important one. So basically, you starting to counting how many constraint you have. So like for this example, I have a 3 constraint. So my dual problem should have a 3 constraint, 3 variables. So my constraint becoming a variable right now. Then, so for the maximization problem, make sure or your inequality constraint are less or equal. So for example, if you have one of these is more or equal, so you multiply both sides with negative, so you will have less or equal. And if you have a minimization problem, when you change it to a dual problem, it become maximization. Make sure all your constraints are more or equal, or you can leave it as less or equal. Then we will have a new standard form we will look at very shortly. So if it was a maximization, it become a minimization. Then like how many constraint I have? So 1, 2, 3. So I should have a 3 decision variables, 1, 2, 3, and their cost or their coefficient will be the right hand side for my equation. So here, if it's less or equal here, so I will make it 100. So this is the coefficient for my first variable. And this one will be 80, and this one will be 40. Make sure this is the same sign over here. So it should be always less or equal. If it's more or equal, you change it to less and equal, then multiply this one with negative to make your solution is consistent. Then the first constraint for your dual problem will be taken from here, from the columns. So for example, for this problem over here, so my first thing, I will look to this column. So 2 will take it from 2x1. Then the second one, I will take the coefficient from the second equation, and the third, I will take it from the third equation. Let's look to the second one so we know what's happening again. So the second one, for example, look to the second column. So like the column become a row. Then what is the coefficient over here? So it's 1. So y1 should have a coefficient of 1. So right now it's y1. Then y2 should have coefficient of 2. So y2. So I don't have over here coefficient for y3, so it's 0 y3. Then look to the signs over this one, so more or less or equal. So you look to the original problem. If it's maximized, then it's more or equal. if it's minimized, so this has become less or equal. So in our case here, I should make it in a more comfortable way. So just one moment. I think this is way better than, so you will notice what's happening. So for example, my first constraint for the dual problem will become 2y1 plus 1y2 plus 1y3, because this is a maximization problem, more or equal, and what is the cost become the right hand side, more or equal to 3. Okay, so then we will do it for the second one. So it will be y1 plus y2 plus 0y3. So this is a maximization, more or equal to. So this is the second constraint. I will go to the whiteboard. So I give you an exercise. So let's consider this a problem. So let's have a minimization of C equals 3x1 plus 2x2 subject to x1 plus 2x2 is more or equal to 3, and then 3x2 plus 2x2, sorry, should be x1 more or equal to 5, and x1 and x2 is more or equal to 0. So here's my primal problem. So I want to change it to dual because it's maximization. So minimization, so it's becoming a maximization of V, for example. So I have here 1, 2, 3 constraints. So I have y1, y2, and y3. So this is the first. I have two constraints. So I have only y1 and y2. So I don't have y3. Then here, this one is a 3. So this is a 3 plus 5. Then here, this is the first constraint. This is second. This is the third. So here, I have it will be 3. Sorry, it will. I will have this one. So 1 y1 plus 3 y2. So this problem is minimization. So it's becoming less or equal to 3. And then I look to this one here. So 2 y1 plus 2 y2 is less or equal to 2. So what is the wonderful thing about dual problem? You can see how is like hard for us, or it's maybe takes us sometimes, because we have here more or equal, so we need to add an artificial and subtract a surplus. So when you change it to a dual problem, so this is the first benefit I can get from the dual problem. It's becoming a simplex problem. So this is easy to deal because here I need only to add slack. So I don't need to add an artificial variable. So this is the first benefit from the dual problem. Of course, so for there is some tricks. For example, if you have an equality, does anyone have a guess if you have equality sign in dual problem, how to change it to dual problem? So if we have an equal sign, so then you will make two constraints for it. So this is will be becoming more or equal and less or equal. So in case if you have equality, you will change this constraint into two constraint, because like if you have two constraint, one tell you more or equal and the second one tell you less or equal, so when you combine them, the logic says it's equal. So to go over this, So you change the equality into more or equal and less or equal, then you reformulate it in the form we will see it very briefly. So for example, we have this problem. This is the original problem. Maximize z equals to 3x1 plus 2x2 subject to 2x1 plus x2 less or equal 100, 1x1 plus 2x2 less or equal to 80. Then we have x1 less or equal to 40. We have the dual problem. So we change it into the standard form using the big M method because it's minimization. So we need to add two artificial variable multiplied by very large number M. Then because it's have artificial in its cost, we know this is a minimization, so we need to evaluate the cost of the production. So to eliminate these two artificial, we from the objective function, we multiply the constraint having the artificial with M, then subtract it. And to be consistent, we agreed to change the minimization problem into maximization problem. So V equals minus W. This is becoming my new system. So this is my new system over here. You can see I don't have non-negativity constraint. So let's see, for example, you have just put it in uh, post optimal solution, or let's say you have just solved it manually. So let's see what is the difference between the primal and the simplex. Of course, we have different decision variables. So here we have x1, x2, and s3 as our basic solution. Here we have y1 and e2. So e2 is the slack over here, or the surplus for the dual simplex. But both of these two problems are sharing, by the way, the same solutions, the same optimal solution. So they both having 180, and here we have also 180 over here. So basically the optimal solution will be the same. Okay, so when I can use the dual simplex method, so there is some, for example, criteria I cannot play with them because it will create some problems if my original or primal simplex method have them. So if like there is not all the simplex primal problems have a dual problem. And also, by the way, so you can extend the same dual problem for any kind of optimization problem. So even quadratic programming or convex programming, they have the same concept. So let's say we having maximization of z equals 110 and 120 x2, but we have minimization inside it. So if you have a contradiction in your objective function, not all your goals to be maximized, you cannot solve this one using a dual because it will create, you will see a looping inside your duality. So it cannot be done. The other thing here, so if you have a maximization problem, so you should have at least one of your constraint less or equal. So you should have a visibility inside it. So if they are or more or equal, then you will not have a problem. Same applies for minimization. So if you have this a problem is minimization, so at least one of your constraint should be more or equal. And also if it's minimization, so all your constraint or your decision variable should be multiplied by positive coefficient. So like if this minimization and one of your decision variable need to be maximized, you cannot apply the dual problem. So this is the correct one. I cannot use the previous one. This one will create invisibility using duality. Maybe it can be solved by the original object like optimization primal solution. So you can solve it, but you want to change it into duality, it will create some problem. So here, when you have a maximization or minimization problem, so to solve it using a duality simplex method, MATLAB have created something called standard or normalized form. So MATLAB have introduced this a problem and have solved it. Of course, there is some previous work on that, but we will stick with MATLAB theorem since we are using MATLAB. Uh, Simplex, also we using Simplex, but by default, Simplex doesn't care about the standard form initiated by the program. So it's basically if you give it the original problem and you call uh, the like the dual problem, it doesn't matter for it, but it's sometimes critical for MATLAB. So when you have a maximization problem like that and you want to solve it using a dual, so the first thing here in MATLAB you should uh, convert your maximization into minimization, so it will not understand that you have a maximization problem. So your cost objective function or your cost problem will become minus 110, minus 120, minus 150. So the first thing is to convert any maximization problem if you are having using MATLAB into a minimization problem. In Simplex, you just can type max or min, so it doesn't care about your objective function. And also the second thing, always change your problem into less or equal. So it will not solve it if it's more or equal. So your constraint should be having always less or equal. I'm talking about MATLAB standard form, not about elsewhere. So like logically, if it's maximization and you have a dual problem, you can just multiply it by minus, and this has become less or equal, less or equal, and you continue on that. But if you're using MATLAB, you should change all your constraint into less or equal. So the first one, I don't have any problem with that. So this is becoming 5x1 plus 3x2 plus 2x3 plus the slack, because I have less or equal, so equals to 100. This creative problem, so I should multiply both sides with negative, so it's becoming minus 5x1 minus 3x2 less or equal minus 120. Because right now my constraint is becoming less or equal, so I just can add s. So originally, if we want to solve it using the simplex method, we should subtract s slur plus and add an artificial. For here, the normalized form for MATLAB, you should subtract only just adding a slack variable because it became less or equal. And also it applies here the same thing here. So this is 1x1 plus 2x3, so more or equal 70, you will multiply it with negative, so it's becoming minus 1x1 minus 2x3 less or equal minus 70. Then because it's less or equal right now, so you need only to add a slack variable. So this is your normalized standard form is acceptable using MATLAB. And by the way, so in MATLAB, for example, you don't need to add the slacks. So because by default, because all your like matrices, when you define the A in your MATLAB, so like these are uh, by default identity matrix can be recognized even if you defined it, so it will give you the same solution. So now previously you should include it, but right now it's more efficient for, I think, like for after 2014 editions, so you don't need to add this into your standard form. So let's see this problem as a minimization. So let's say how the MATLAB can read it. So it's basically was a minimize C equals 45x1 plus 60x2 plus 75 subject to constraint. So here I having only problem with the third constraint because it says is more or equal. So I multiply it with negative. So I don't have any problem with the objective function because originally was minimization. So it's right now becoming the same thing here. But if you want to solve it using MATLAB, if it was a minimization problem and you don't want to stuck up with invisibility, make sure the original formulation of your problem having more or equal, or if it's or your constant are less or equal, so one of the your right hand side have a negative value. And the same applies for maximization. So like in maximization, make sure or like at least one of your right hand is positive, or when you formulate it, if you have many more or equal, so at least one of them is less or equal, so you can apply dual simplex method. So let's have this a problem. We have seen it before in the sensitivity analysis. So we have a maximization of z equal 100x 1 plus 120 x2 plus 150 x3 subject to 5x1 plus 3x2 plus 2x3 less or equal to 100, 5x1 plus 3x3 less than 120, 1x2 plus 2x3 less or equal 70. I have told you in the sensitivity analysis class, we want to change the right hand side for the third equation to be 20. So like in that, if you remember Monday's class, so this one have been changed from 70 to 20. And for example, an engineer found like in his inventory, one of his material is depleted, or maybe like they didn't make an purchase order, so they were predicting it will have 70, and because of some events, so they didn't deliver the shipment. And then like he has in his mind originally to create x2 and create x3, so like he know these are will be his like his objective or his decision variables to make, or and he knows the basic solution of them. Then like for using matrix form simplex, he create this one. Then unfortunately he found out that x3 is invisible in this scenario. So since you have this one in your solution, so previously we cannot accept this format, but in duality this is acceptable. So this is the gain, or this is the benefit from using the dual problem. So when you stuck up with this minus, then you will consider this one should leave my matrix. So previously our optimality condition was over here. So to know the optimal solution, Zj, this row should be more or equal to 0. If you like if you use a post optimal solution, and you, for example, you just want to allocate x1 and x2 in your production, then you want to find out if it's visible. So let's say this is a trick. Then you find out one of them using the post optimal solution is not optimal. So you don't just stuck at this one. You don't need to reiterate again from the beginning. So you just take this negative value and assign it as a leaving variable. So previously we just in the first step assign the entering variable. Then we decide if it will replace one of the resources or one of the variables. Right now, your first decision is which variable should be leaving. So you decide x3 shouldn't be included my production plan. Then here, the second step is basically you will divide this value. So you will divide 10 over what you have here in your row. So you will divide 10 by minus 1.25. Then you will divide 10 again by minus 0.25. then you will divide 10, etc. will all the coefficient inside row. So previously, if you remember in simplex method, we dividing the right hand side by here. So here it's same. So you're dividing the right hand side by the coefficient lies in the column. But this time you fixed the right hand side, then you just change the coefficient. Previously, we changed the right hand side, and also we taking the uh, related coefficient. Here, no, you just use the same right hand side, so you fix it, then you divide it all over all the coefficient, and you can put the bottleneck coefficient ratio over here. So you just look to the ones have a positive value. So like 10 over 1.24 equals 8, 10 over minus 0.25 equal 40, minus 10 over 0.75 equals minus 13 and a third, minus 10 over 0 equals to infinity, etc. So you just ignore any value like a 0 or infinity, so you just ignore them and just look up to the like least positive values. So we have here 8 and 40. So you're taking the least ratio. So this is 8. So this column becoming your entering. So this is the entering variable. So what is right now you are telling me that x1 should be including in the production instead of x3. So I should start producing x1 instead of x3. So maybe my solution will be coming visible. Does anyone have an idea how we can iterate for the next tableau? This is a bonus question. Does anyone have a hint how we can iterate to the next tableau?
Switch it to the dual somehow?
Hmm?
Switch it to the dual somehow?
Yeah, this is the duality. So what is the difference between dual and simplex? In simplex, we just ignore anything negative, and this should be always positive. But like here, because you know in duality, you don't have non-negativity constraints, so you don't have a problem having a value here is equal to any value. So you don't have any restriction over here. So you can pick this one as a pivot row, then pick this one as a pivot column. Then you want to replace this one. So all this, all this row over here should be divided by minus 1.25. Then you want to nullify other values over here. So this one should be 0, this one should be 0, this one should be 0, and this one should be 1. So to make it 1, I should divide it by minus 1.25, then divide the whole row by 1.25, then x3 becoming x1. So there is two ways to iterate for the next tableau. The first one is just to use the original simplex method. So basically you will divide this row by negative 1.25, then you will have the new pivot row, then subtract the other variables from this row. So for example, you multiply this one by 2, then subtract by this one, also multiply this one by 2, then add them together, and also multiply this one with 4 and then add them together. Then you will have the next iteration. The other way, which is the easier way, x2 will remain a basic solution, and S3 will be remain a basic solution, but I will change from x3 to x1. So what I gonna do, I will update my post optimal matrix. So here I will go to MATLAB. This is the easiest way. You can do it either ways. So then I will B, I will not change anything with matrix B. This is the right-hand side matrix. I will not change it. But the CV matrix, which is like the basic solution from previous lecture. So CV will be here. I will denote it. So the basic solution objective function coefficient. Maybe I will update the matrix and send it to you. So like I will send this notes for you. Then you will update the non-basic solution coefficient. So this is the non-basic. So here, objective function coefficient. So basically in this matrix, I have picked x1. So the coefficient for, or the cost for x1 was 110. The cost for the second one was 120. And S3, sorry, S2 is still non-basic, or like it doesn't have any contribution for my objective function for 0. I know X3 have been leaving. So 150 is the profit for my third decision variable. Then S1 and S3, which not contribute. Then here, basically, I will update matrix B. So matrix B is the technological coefficient for the basic solution. So it will include X1 and X2 and S2. So I update this matrix. Then I update this matrix again. So this is for the technological coefficient for the non-basic solution. Basically, then run the code again. So let's see what's the code given us. So this is the shadow price for the technological coefficient for the non-basic solution. And this is the optimality condition. So you can see the optimality condition says it's optimal. So I have reached out the optimal condition. Then H3, basically from previous lecture. So this is the value for X1, this is the value for X2, and this is the value for S2. So then I update the matrix. Finally, here my objective function. So this is Z. So let's see if my solution was logical or not. So there is two ways to reach out from this matrix to this one. So basically you pick this one as a pivot row, then you calculate the ratio. So like dividing 10 by all the rows over here, then pick the least ratio. Then it tells you you should replace x1 by x3. Then divide the whole row by negative 1.05. So this is becoming 1. Then like do it all over again. So this is basically the first step. You can you should do it over here. So this is the first thing. Or you can just do the most optimal solution, which I have done it over here. So this is the most optimal solution. So I just using the matrices and replace x1 by replacing x3 by x1. So x1 will have a coefficient by 1 over here. So it became from the identity I have removed it. So x3 right now is becoming the non-basic. I knew the solution was optimal. So this is the identity matrix for the optimal solution. So x2 equals 8, x1 equals 20, and s2 equals 80. So let's see the logic behind thing. So originally I have 70, but my resource was depleted. I have exhausted, and right now it's became 20. So basically, because if x3 was kicked from my solution, So x3 was kicked. But here x2, I have like enough resource to make 40. But because this a new strategy, look to what happened to x2. X2, I have right now lesser amount to do it. Let's just double check if it's this one is from the MATLAB, this x2 or x3. Sorry, so this is should be the value for x1 over here. This is x2, so x2 is 20. I will update the share the slides. Okay, so this one is becoming 20 and this one becoming 8. So what's telling me right now that I have less resources, so my production plan will be reduced. So I have to produce 20. Previously, it happened if it was efficient, I can go up to 40, but I don't have this privilege. So my objective function, for sure it will be reduced because the price for x1 and x2 are way less than the prices for x2 and x3. So I have also, because I have less resources, so I will make less production amount. So this is the logic behind that. So the thing I want you to learn, if you have like an post optimal with a negative in right hand side, because the duality allowed me to pick this row, so you will not stuck up with this iteration. You can just proceed to the next one by picking this one as a pivot row, and then find out which one is the pivot column. So why the dual simplex method says the objective function should be not contradicting. So all your objective function should be maximization. So in case, for example, one of your variables, let's say in a minimization. So like these two are maximization and this one is minimization. So in this case, if this is not optimal, so you need to loop again over here. So you have here two loops. So this is will contradict itself. So you don't know how to go. So like, for example, you go over here and it's tell you you should pick this one, but this one is tell you go in this direction and this direction is invisible. So it's contradict itself. So your objective function optimality condition should be similar. You shouldn't have, for example, a maximization here, then a minimization over there. Okay. So any questions for the duality? Okay, thank you. Great. Okay.
I have a quick
Yeah.
question. So is this general duality, or is this a dual space as in a vector space?
So this is a generalized duality. So there is three benefit from dual simplex method. So the first problem is when you have a minimization problem, or when you have an artificial variable problem, and you don't want to have an artificial variable. So the only thing is, because basically the artificial variable will increase the size of your matrix. Like imagine if you have a problem with, let's say, thousands of constraints, which is in real life application can be applicable. I work with the industry, have a 10,000 different product, which is like as a daily production, because they have a like a sand casting production line, and you know how heavily this kind of production line will be customized. So basically they have a many constraints as well. So if we want to apply simplex method and we want to stock up with artificial variable, at that time I think I worked in 2007, something like that. So we don't have the good machines as we are having today. So these problems were nightmare for us. So the duality is change the way we look to the problem, so you don't stuck with non-negativity solution. You can just, for example, when you have this problem over here, so like let's say you have a negative in one of your right hand side. So like you having this value over here, -1. So basically in previous solutions, you will consider this one as an invisible. Why? Because if you don't want to start from the beginning, let's say you having a production line for day one. I'm telling you like what was happening with us. So I have the production for day one. It was x1, x2, x3 up to x10. So we don't want, in today's production, we want to create from x1 to x6. So we know these gonna be in our production line today. So when we put them inside matrix, like this kind of matrix, so you don't need to start from the beginning. You just put in like MATLAB, this is gonna be the basic solution, and give me the if they are optimal or near optimal. We were not like very critical about the optimization. Like if we have a -10 or something very trivial, we can go ahead with this production plan. But let's say, for example, the second day you want to exclude x3 from your production line and put x7 in your production line. So instead of just scrubbing the whole production here, you just swap. So like you will have from x1, x2, x3, then x4, 5. Then you don't have 6. You will just add 7 in your production line. So basically you will put them over here. So then you will check up if your solution is optimal. So previously we don't have this one. So it give you like if you have a problem over here, it's okay. So like you can argue with management about how much you will lose if you stick up with this method, but you don't allow anything over here to be minus, because this is says invisible, like the production line cannot produce this thing, or you should, for example, disassemble this amount, which is not logical. So the duality give us the privilege. So it says, yeah, this is negative, so go back over here, see which product you should not making today, if your manager allows you. So it says this one should be included in your production, excluding. So x3 is not visible. You cannot, with the resources you have, you shouldn't do that. So then it's tell you which product, or for example, what resource you should utilize more. So you go over the next plan over here. So maybe x1, if I produce a small amount of it, doesn't harm here. So maybe 8 is good. And there is many other consideration, like in real life situation, you cannot just like iterate from beginning. Even I will address it also in the integer programming, which is our next topic. So you cannot, for example, always rely on simplex, like doing simplex all over again. Sometimes you just need some kind of rounding. You will be okay with it. So this is the good thing about duality. The duality, when you have a let's say a negative in your right hand side, so you can just fly from it. And also the other thing, which is initially was started when you have a minimization of problem with more or equal, and some people doesn't like the computation of artificial because it will, increase your matrix. So like your matrix will be very large. So the duality have solved this problem as well. So like instead of having, let's say, up to 10 variables, or like your matrix will be at least like 1/3 size of your original matrix. So this is like compress your matrix. Okay.